We've got 3 more examples for calculating the pH of a weak acid or a weak base. And I'm going to move through these examples a little bit faster and with a little bit less explanation than the first video, but we're going to follow the exact same steps. So the first step that we have to take is writing a balanced chemical equation, and we're going to rely on the problem, the words in the problem, to help us figure out what type of equation we need to write. So first of all, we know that one of our reactants is H2CO3. H2CO3. And I told you that the other reactant always is going to be H2O every single time. So getting your reactants should be pretty straightforward. The next thing that we have to do is predict the products, and the products depend on whether the reactant is an acid or a base. To figure out if it's an acid or a base, we're going to look at Ka or Kb, the equilibrium constant. If it is a Ka, like it is in this case, Ka means that our reactant is an acid. And when our reactant is an acid, one of our products is H3O plus. Where did the H3O plus come from? It came from moving one of the hydrogens from the acid over to the H2O. So our other product will be HCO3 minus, which is what we get after H2CO3 loses a hydrogen. So step 1, balanced equation is done. Step 2, we need to make an ice table. The ice table, we're looking at the initial amount of H2CO3. The problem tells us that initially we have 5.6 molar, and initially we don't have any products at all, and we're not going to worry about water at all in this problem. This is a weak acid, so that means we don't know how much of it reacts. Some of it reacts, but we don't know how much, so we're going to say minus x. We're going to look at the stoichiometry in this equation that we wrote, and we can see when it's balanced, everything is 1 to 1 to 1. So if we have a minus x, that means on the other side of the equation we have plus x and plus x. And at equilibrium, our concentrations are 5.6 minus x, x, and x. And again, always, we are going to assume that x is very small compared to 5.6. So we're going to assume that 5.6 minus x is just equal to 5.6. The next thing that we have to do is write our equilibrium expression, Ka. Ka is, actually I'm going to write it up here. Ka is our products, H3O plus and HCO3 minus, over our reactant, H2CO3, leaving out water because it's a pure liquid. We know the value of Ka. The problem tells us that Ka is 4.5 times 10 to the minus 7. We know the value of H3O plus. Well, we don't know it, but we're calling it X. And HCO3 minus, we're also calling X. And H2CO3, we're calling 5.6. Again, let's just take a look at where those numbers come from. HCO3 plus is right there. HCO3 minus is right there. And H2CO3 is right there. So now all that we have to do is solve for x. 4.5 times 10 to the minus 7 times 5.6 is equal to x squared. X is 5.6 times 4.5 times 10 to the minus 7. Take the square root of that. and we get 1.59 times 10 to the minus 3. If you want to look at the approximation that x is very small compared to 5.6, this approximation that we did right here is extra valid in this example. If we rounded our answer back to 2 sig figs, we would end up with 5.6. We are now ready to calculate pH. The pH is the negative log of the H3O plus concentration. The H3O plus concentration is X, negative log of X. X is 1.59 times 10 to the minus 3. The pH is 2.8.